and Twitch at the same time. It seemed to be working so far. However, yeah, it's pretty decent. Just gonna share the stream in the Discord. And we are ready to go soon. Where? Oh, Olodie. There. Okay, so welcome to this stream where I'll be building, or at least start to build, triple Trinamic TMC5130 motion controller board. It looks, yeah, let me see if I can upload an image of it. No, I can't, but the image is on the YouTube link. This is just like a render I made in Fusion 360. I'll share it to the chat there. And okay, so if there's anyone at the YouTube stream and I'm not able to follow the chat, yeah, I guess you can't pray or something. Okay, so let's get to work. For some reason, the YouTube stream looks inverted. So if someone is watching YouTube, let me know if it is. Okay, let's go. Let me pull up the same browser window. The Trinamic. There. Okay, so finally, I'm going to work with these stepper controllers again. I have actually already built at least 2 different ones from Trinamic before. A TMC5230, which is like the replacement driver for the Polulu drivers on all stepper, those tiny stepper motor boards, which have been sold for several hundred centuries. And also, I have actually made another driver with a TMC5130. That one has a lot more details than I have now. It has like flyback diodes and a bunch of other stuff, which is nice to have, but not strictly needed in terms of the power levels I'll be doing here. So what I'm be doing here is actually copying the Trinamic TMC5130 BOBs. Bob is a breakout board. And you can see that design here. It doesn't have that many components, thankfully. I'm not sure if this uses the method with sensing resistors for sensing current, but I guess we'll find out. So first thing I'm going to do is, yeah, we can look at the specs. So it can work on voltage from 475 volts to 46 volts and 1.4 amps. So if you're good with math, 46 times 1.4, so let's say 50 volts and 1.5, that's about 75 watts. So between, let's say 65 watts, something like that. That's a pretty decent amount of current for this little board. So we'll see. I have created a new PCB for it, like a template, which I have created in Fusion, which is the base of the other board, or the board that I shared through the YouTube live stream. So yeah, if you're not subscribed to the YouTube channel, you can do that if you want instead of Twitch. I'm going to try to stream to both at the same time because I think they have quite different audiences. Yeah, we'll see. Also, the live streams are searchable on YouTube as well afterwards, so they will be a part of the YouTube ecosystem. So let's download the files here. So you have schematics, and you have something called fabrication data, and you have CAD files. So let's see. I have downloaded these before, but I'm just going to download them again. And I'll see if I can share some of the files here. I'll try to open them in the browser. I'm just going to extract them off screen here. Okay, so they have quite a different structure in terms of what types of CAD software that's been used to create the PCB or the EDA software. So let's head over to EASYEDA and see if it's possible to just import the entire thing. EASYEDA Designer. Yeah. This is how the tiny Pico board ended up after I remade it. I don't think I shared my last version. It ended up pretty cool, pretty good. Got some decent routing on the of the power here. Yeah, you can see not very clear, but I think, yeah, maybe blue one is to see it. So yeah, obviously I'm gonna order it black. I'll be sharing all of this stuff for free. So the software that I make on, not the software, the software true, but the stuff that I make on this channel will be freely distributed for everyone for free. And I'm actually going to try to make a good deal with Jlcpcb to see if it's possible for people to order some samples of these boards for free. That would be great. They contacted me after some other boards that I made and said that if I wanted, they could send me free boards as long as I shared Jlcpcb. They showed off one of my PCBs on their Instagram page, and they had some good traffic for that. So I'll guess they have faith in that I'm able to do it several times. We'll see. Okay, so let's try to import this into EASYEDA. Okay. Import DXF or image. Okay, I'm not going to do that. Export, file source. Okay, I guess it's open. Okay, open EASYEDA, Ltm Eagle KiCad. So I bet that a professional German company, which are listed on this, no, it's not listed on the stock market, but at least that's owned by a gigantic company, which are, they probably don't use Eagle, probably don't use KiCad. They probably use Altium or something other things, which is super expensive. So let's see. I'm going to try to import the files. Okay, so it's the only thing it finds is folders. Okay, So PCB dock. Okay, so it needs to download these raw files. Okay, but I guess, yeah, looks right. So they have actually both. Let's open this and see if whatever happens. Okay, import Ltm file failed. The file needs to be an ASCII file encoded UTF-8. Okay. All right. I guess there's some stuff going on here. Maybe it's like European ISO standard or something. Let's try to do the same thing with the schematic. Okay, needs to be an ASCII file encoded in UTF-8. Huh. Let me Google that. EASYEDA import Ltm UTF-8. Problem. Okay, there is something here. Advanced schematic, ASCII binary. Yeah, okay, so I guess that it's saved in binary. So it's kind of too late. I guess that sucks. So let's see if it's possible to... Convert it with some online tool. Convert Altium to ASCII. If that's possible, probably need like some kind of tool. Yeah. How does these files look anyways? If I would look right, just at the file as text files. If I'll just open them in Notepad, let's see if that's possible. Yeah, so they're a bit just very basic text files. So should be possible to just convert these. Just line by line text files. Huh. Yeah, it also has the name of the user who made them, Katsutaya. All right. Okay, so let's see if we can import Ltm files online to see if there's some. Yeah, there. Let's see. Download CAD files. And yeah, I can upload everything here. Maybe I can try to upload even the zip file here. All files. Maybe it's smart enough to unpack it. TMC CAD files. Okay. It will take a few moments. All right, all right. Seems to be working. Yeah. Pretty horrible 3D shot. Well, that's fine. Oh, they even have a bomb. Okay, so let's see if it's possible to... Okay, anyone can share. Okay, can I download it again? Maybe not. Embedded, embed. Layers. Oh, I guess not. Copper. Okay, at least we can see the different layers, but we can also see that and the so we can turn these on and off. Okay, so this is oh yeah, this you do it like that. Okay. Let's disable the paste, the bottom, and the multi-layer. Okay. Good. Let's look at the top one. Okay, so what I think is interesting here is just to see how they have solved different things in terms of how things are rotated, how they route power, where they place the decoupling capacitors. Let's see if I can do some. I guess maybe there's like a button to rotate this in a nut. Oh my god, this is quite annoying. Okay, there. Okay. Okay, cool, we can zoom. So they also have a ton of vias under here, which is interesting, and they don't have any windowing. So if you have these vias and they're not filled, you're definitely going to have a lot of solder filled into these vias. So I will not be breaking out the stuff here, all the pins, the same way as they have done here, because I'm obviously not making a pin header board. Okay, let's see. Where did the layer there? Okay, so yeah, this is a normal ground layer. So they on top they route all the signals and low power, and they probably do all of the high voltage here. So this is the motor current. Motor current. The motor traces for the high voltage stuff. And at the bottom, it's oh, interesting. Yeah, so this is okay. So this layer is a ground layer plus the input for the motor goes here, and then you have this layer is the output from the chip to the other pins. And I'm not sure. I don't remember what these are. Probably some enable pins or something like that. Let's see. Is this the schematic? I guess it's like one of them. Maybe there's something I can click to see that. Oops. Okay, so this should be quite easy to adapt. Let's look at the components. So there's some filtering capacitors and some more filtering. And that's it. A few resistors. And the SMD chip resistor 0R. So this is basically a cable or a chip without any resistance at all. And it's used to, I think it's used to control if you are using the UART or the SPI, I think. I'm not sure. Okay, so let's head over to LCLC and have a look how much this chip is at the moment. So at the moment, this chip is absolutely ludicrous expensive. So remember this one. So it has gate MOSFETs or built in. So it doesn't need MOSFETs externally on the outside. And that's like the main big difference between the 5160 and the 5130. 5130 obviously does a lot less power, but like the main structural difference for it. Something which is a bit funny is that, yeah, these prices changes all the time now because of the semiconductor horror story, which is happening around the world. And LCLC, which is a Chinese company, have algorithm. I think they have like algorithmic. I can't even say that word. Algorithmic pricing. It's like when Amazon started selling books and started to compete, and suddenly there was like this $20,000 book or something because everything was done automatically. And these prices really fluctuates a lot. So if you go over to Jlcpcb TMC5130, we'll see that the price is not that bad. Yeah. Except for it's no longer in stock. And it's $6 if it were in stock. I could buy a tape and reel, 2,000 of them. But I guess. Okay, lead time 6 weeks, so that's not too bad. Other stuff has like 40 to 50 weeks these days. They might have them on other places. Octapart. We can use Octapart to go and check out multiple at the same time. TMC5130. See if anyone has them in stock. Yeah, it says that the Jlcpcb has the Eval kit. Okay, so let's see the chip. It's empty everywhere. So why am I making this then? Well, I'm not empty out of these chips. I still have some. And these are quite easy to make. So what I'll be doing for the next board, I will probably be making a TMC2109 with only a UART chip. So it will be like a super low power, but very small format USB driver, which you can control from a normal computer. I'm going to use this for turning very small motors, like adjusting focus on camera lenses or other stuff like that. And I don't want to have, something big or like a complete board, because I'm just going to run it off 5 volts. It's not going to spend a lot of power. So, yeah. Okay, so first, let's go over to the circuit search stuff that I made. So this is a web page, which it has all the designs from EASYEDA or Open Source Hardware Lab, OSH, whatever it's called. from EASYEDA, and it has, there are basically 3 different search engines. This one, which is called Circuit Search, it's quite confusing, but I don't care because I mainly made it for myself. For now, circuitsearch.marishair.com. So this uses a normal full text search. You can use and plus operators. You can also do local data sorting. Default use, views, stars, and comments. And it has these tags which automatically takes all of the parts which has the designator queue. It kind of works. And you can also click these here. It's good. It's pretty fast. Pretty fast. And then we have this one called -human. This is kind of the very bare bones that I made. It uses a very basic regular search that searches the entire HTML of the page. This is like 100 lines of code max to do everything, or maybe even 50. So let's see 5130, see if there is anything. Okay, so there's a Mechadunio. Let's have a look at that. Maybe I can check the... Yeah, I think it's pretty quiet on the YouTube chat. Yeah, that's fine. Okay, let's check out the Mechadunio alt. I guess many of these designs doesn't have names which were meant to share. Okay, so a fancier Mechadunio, maybe. So let's have a look at this. Something which is kind of great now is that I can quite easily get all the components I need. And I don't have to spend that much time searching for stuff on Ltm. But yeah, we'll see how much we'll use. And it's also nice to see, you know, maybe this is made with a 3-layer board. Let's try to open it here in the Mechadunio alt. What is that? Mechadunio. It serves like it's probably like Arduino, obviously. Let's try to do a search for this. Okay. That didn't make a lot of sense. Oh, yeah. Okay. I guess this does. So it's basically an Arduino-based shield which sits on the back of an EMA 17. I have been thinking about making these, or these kind of style of boards, because it's quite convenient to just smack them on the back there. However, I'm also interested in making some Wi-Fi versions of these. So if no cable at all. And that might sound crazy, but the fastest interface on the ESP32 is actually Wi-Fi. And I have actually tested it, and it works quite well. Okay, let's check out the 5130 design here again. Let's open the editor. So it uses a Hall sensor here. AS5472, let's have a look at that. Okay, it was not an LCC, so I guess they don't source. Holy moly, 87 kroner. That's like $8. And it's made by AMS, same company that makes the LDO that everyone uses, I guess. This is like real, this price? Or was it just like 1? So yeah, $7. On-axis magnetic rotary surface mount positions. Okay, that's interesting. Something else that I actually want to create as well is I want to see if it's possible to make my own encoder. Because what I've noticed, so I want to make one based on the circuit board. And at first, you might think, oh yeah, because you can use like the sales screen to form like a white pad. Yeah, you can. However, what you also could do is that you can make a whiteboard or black one, probably better with a black one, and then you can use. Actually, let's go on a tangent and just do that fast and see if we can just illustrate what I'm talking about. So let's pretend this is an encoder. It's going to be 30 mils, something like that. Not mils. I just like call it mils, but it's not mils. It's millimeter. Okay, so if we go to the possibilities tab on Jlcpcb, we see that the minimum trace width is, did I miss it? Where is it? So the dimension tolerance is 0.2. Thickness tolerance. Minimum clearance. Pad to pad clearance. Okay. Pad to pad clearance, 0.127. I think that's like the smallest. Okay, it's on 4 and 6 layer board, it's actually 0.09 millimeter. Why would I be interested in that? Because, so when you do the silk screen, what they do is that they basically create like a solder stencil and they just pour paint on top of it. So it's not super accurate. However, when they make the circuit board, they use photons or light to expose a special film that is on top of the copper. And because it does that, it makes very accurate edges and stuff like that. So if you want to have like small contour stuff or small graphics, use exposed copper instead of using silk screen. So what we could do is that, so let's say it's 0.1 now. And let's do snap size 1, and we'll do grid 1. Something like that. And we'll move this to center 0 and x0. There, we'll move this outline. Now I'm going to select this as an outline. There. Okay, so watch this. I guess I'll have to turn on. Maybe I can just copy these and rotate it. Yeah, it only rotates by 90 degrees. That's fine. Okay, let's not be too detailed. I guess I can show the principle quite easily here. Free angle. Okay. So an encoder is a sensor which, well, there are multiple, but that's oversimplified stuff. For the motor to run as efficient as possible and to actually control how or when you're gonna power the coils of the motor, you need to know where it is, or you need to guess where it is. Or you can measure something called the back EMF, but let's not talk about that right now. So imagine that the controller needs to figure out where on this 360-degree travel path of a motor it is. Is it at 3 o'clock, 6 o'clock, 9 o'clock, or 12? And then you have these encoders where you basically put like a sensor here that reads off the pattern and creates a small pulse for each time one of these here passes. Oh, an arc. Free angle. Like this. Okay, so now let's do this, and I can do expose copper like this. Now watch. Maybe I need to save it. The wind is insane today. Okay, so yeah, obviously I could just also use like small dots like this. I can just add, if I do snap size 0.25 or something. Something like that. This is going to be horrible. I probably wouldn't create this in this software, but you kind of get the point, right? And I'm going to expose this here. Okay, you need to expose them one at a time. I remember now. Actually, I can just use a pad like this. And I can do a top one and make it 0.2 or something. There. Yeah, it's going to snap in a non-great way, but doesn't matter. And now, I guess you can see it's better. Yeah, see? And if I just make it the absolute smallest, I can also completely remove this. So I can do just copper. And I can totally remove all of the copper. So I only have these points here, which could either really left black or blank or just with copper. And that was probably going to work. And I could add an optical sensor that could read this. That would be a super, super cheap encoder, because these encoders are extremely important in terms of moving motors in a proper way. And even though it wouldn't be absolutely insanely great, it would still be a super low-cost encoder, which would help a lot. Okay, let's finish that stuff. Back to the TMC5130. By the time I'm actually going to start working on it, I'll probably be too tired and I have to rename the stream. Or not. Okay, let's make a new project for this. New project. Marius Air TMC 5130. Okay, then I'm going to add a modular CNC triple TMC 5130. Something like that. Okay. Now let's find the footprint for it. So for now, I'm just going to use the LCSC footprint for it. So let's find, where did the page go? LCC, there. TMC 5130. Normally, I would be doing this with like a split screen setup, but that would make this stream not work. So I guess I'll be clicking a lot more. Maybe I can rearrange these a bit smarter. There. 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 And there is my schematic. Go to library, search for the part, and then do search. And there we have it. I usually like to make my own schematic symbols because like many of these auto-generated ones really suck. And I probably already have one, but I'm not going to find the custom one right now. So this one is also using the same. We'll be just using this for now. And let's open the schematics file in the browser. Or the schematic for the Bob. If we can find that. Where did it go? Okay, is it in the CAD files? Nope. Then it's in the other folder, I guess. I have already opened that. I guess it's not great to just watch the, because I'm not able to share. I could do like a full screen share, but I will just share everything, and that will make things really messy. Okay, let's TMC 5130 Bob Schematic. And let's add PDF. Don't even need to spell it remotely, right? And yeah, it has to have PDF. Yep, I guess. This is the one. Rev 10. I'm just going to be lazy and think that doesn't have any important changes. Okay, so see, this is actually a lot better. The reason why I think this is better is that this symbol has structured thing in a nicer way in terms of what makes sense. You see they have all the stuff that's going to ground this close. And let's head over to the Trinamic site and see if we can find, Because if we go up here to, it is actually, if we click the, it should be, yeah, we actually need to go to the chip itself. Yeah, 5110, TMC5130. And there we will find a link to a server. Configure your symbols. See, here is everything. It has the right footprint. It has this nice thing. Choose CAD format. I think usually I select Eagle or KiCad. I'm not sure. Let's see. Download. And then we'll import it. Your Ultra Librarian download is being processed. This is like a second service which lives obviously inside Schematic page, but you can go and visit the service, and they have a bunch of other stuff as well. Ultra Librarian. Here. It's pretty cool. Let's import it. Import. No, actually, let's open it is the right word. There. And it was called UL. There. Oh, yeah. Extract, import file, and extract libs. You need to do both there. There. Add to library. And now I can click this, go to the library, go to EASYEDA, and I should find these somewhere here. Actually, I think I should search for it. Yeah, there it is. Please. Perfect. Makes it a lot easier to implement the design similar to what's in the BOB. So these BOB designs, or all of the evaluation boards from Trinamic, is open source, and you can copy them, do anything you would like with them. So let's have a look at the component list to see. So I'm going to try to select parts which are in the library for Jlcpcb assembly service. However, the search bar for this, not search bar, whatever. Yeah, you understand. Here is horrible. Horrible. But we'll manage. Let's just close this for now. And this. Okay, so where should we start? So usually I would start to just read the entire schematics for this. Then I would read the schematics for the 5130, the chip itself, and I would probably read it for a long time. It's probably over 100 pages. There's a lot of stuff to digest, and these schematics or the data sheets, I mean, they kind of are written over several years as well. And sometimes they just put like super important stuff that you wish that you had seen later at the very end or something as like a revision. So just don't read it precisely, skim for everything, look for important things, and just look for example circuit or like the minimum thing you need to do. That's both when it comes to code, but also to like example code. So like the initialization and the stuff to have the smallest amount of task you need to do in terms of creating a test board or something. So for this, you see it's not a lot of parts. So it has a bill of materials here. I can go and automatically import this. However, I'm probably going to go for this piece by piece or part by part or whatever. So it has first the good old 100 nanofarad capacitors for decoupling. 0603 footprint. Let's go over to this. And this is almost the example. It's the example search here is a 10K resistor. So let's do 100 NF 0603 and probably get like one part. And it's also important that I click basic parts. See? So we have only the Jago one. And usually these standardized parts, you can click it and you don't open it in a new window. They are 50 volts, which is great because when the higher voltage ones have a tendency to have lower ECR. They can handle more heat. And there's very few reasons not to select a non-50 volt one as a normal individual. Because, you don't want to have stacks of different 100 nanofarads capacitors laying around. So we'll just use this. So let's import this. We'll copy this. Import it in here. Library. Oops, we didn't get the part number. There, let's search. Yeah, they have several in stock. 5 million. So we need 4 of these. So for now, we'll probably not care too much about where we place it. So I usually place this stuff here like this. Can even remove this for now. Because I just want to make sure I have all of the different components. Sometimes I even just import one of them and just keep a row of all of the components up here. And I just copy them when I do the circuit. But this one has very few components, so it shouldn't be a problem to do it like this. Even I can do that, I think. So 22 nanofarad. Let's see if they even have that. Yep. Samsung. It's cool. 50 volts. And how many? I guess 1. Okay. So I'll be making just 1 bob first, and then I'll just copy the entire circuit. And then we're going to switch out the cable select pin, because they will all run on the same SPI bus, but they will have a different GPIO pin for the cable select. And if we do it like that, we can control all 3 with just 1 microcontroller, or through the USB from a normal computer, which is the main goal for this. I want this board to drive really small machines. And I'm also going to add like dip switch for this. So you can actually run 6 drivers. Probably not 9. But 6 is enough for a small machine. Because this machine doesn't need to be big in size in order to need 6 drives. It could just have, could be controlling focus on cameras, and small stuff like that. Okay. 470 nanofarad. No, just make sure that it has the right footprint. 0603. I wonder if we're going to run into not having a component. Nope. The good thing about using this is that they're almost free to place. But if you're going to place something which is not part of the basic part library, you need to pay $3, I think, per place. Doesn't make things extremely expensive, but let's say that if you're building like a TMC5160 and you have some big MOSFETs there and they cost $3, $3 is going to add some cost to 8 MOSFETs. Probably double the price of all of the components. Okay. What did I do wrong now? So, okay, I think I know what this is. Because when you click library and you do this, and you forgot to search, it still has the old one. See? Let's just make sure that this is also 50 volts. I don't even remember if I checked that. It's 25 volts. And is that going to be a problem or not? Well, that depends on what this is used for. So we need to figure that out. So it's component number nothing. Doesn't say. That's weird. Oh yeah, I guess it's on the board that I removed, or the web page. I mean, okay, not there. Let's look at the Mechadata board and see if we can find it there if it's used. 470. There it is. So this is used on the 5 volt out. So it's not going to be 50 volts. And there's a reason why. Because you almost never use 470 nanofarad with a 50 volt power. Okay, so we're good. Yeah, and I have already done it. So the next one is 4.7 microfarad. I guess this one is used in conjunction with the 471. Let's see. Yeah, it is. This kind of values usually, it's either 10 micro or 4.7 for this kind of job. Did I search? Yep, and let's see if it's 50 volts. Nope, it's 16, but that's fine because we're not going to use it for the high voltage part. There. Place. There, C7. Let's, yeah, they didn't have the C7s or whatever here. And then we have 4 1206 10 microfarad ones. This, I'm probably going to do a bit different. So you see, these are 35 volts. And this board, supply voltage 5 to 46 volts. That's not good. Okay, this is a revision 10. Maybe let's not look at the later revisions to see if they change that. So capacitors are cheap, and adding a bunch of capacity to this high voltage rail is not going to be any drawbacks if you use like too much. So let's do it a bit different. Let's open the parts catalog there, and then we'll go to capacitors, and we'll go to ceramic. I really like the way they have this design here. Makes it almost impossible to read it in a nice way. Everything's just floating, and it's a disaster UI-wise. There, multi-layer ceramic capacitors. And let's see if we select 50 volts. Let's see what we got left. So the max one is 1 micro for 50 volts. Let's reset it. So you can only select one at a time. You can select several at a time if you have a different one. So yeah, so now we can, so I guess if I click 35, I'll probably find 10. Yeah, see? So I could limit the input power for this board to be 35, or let's say 30 volts. And I can use the SMT assembly. I can also add the other capacitors as part of the extended library, but that's going to cost $3 per part. That's not good. So let's see, what's the highest capacitance we can do here? 50 volts. It was 2.2, wasn't it? 2.2. Let's have a look at that. See, nice, beefy. And how many? So they use 4. So we would use, in order to have the same capacitance, we would need to add 16 of these. We might actually do that because it might be cheaper. But then, see, extended part. I forgot to click the basic part. So there's nothing. Basic parts. If I want to have 10, I have 35 and 10. Yeah, maybe Trinamic uses the service to make this. I'm not sure. Okay, let's have a look at the basic parts again. And then we could also use other capacitors. We could solder these capacitors ourselves. That's quite easy. Especially if we would use big ones, or electrolytes, or both. Let's check S&D ones, but I guess they don't have any. Yeah, they don't have any S&D based electrolytes. MLC leaded. Oh, they actually do. Oh yeah, it's these. Okay. So let's go back to multi-layered ceramics, select 50 volts, and see what we end up. Like, is there even anything here? Which is not small, but also is in stock. Yeah. I like the way that the description name has, like, yeah, this, which you don't actually need to see. 100 pico, 1 micro, okay, 33. Okay, so this is what we're going to do. We are going to add the 1 micro one. And we are not going to add 40, but we are going to use these in conjunction with some electrolytes. So if you are running this board on, very low power, this is going to be fine. If we, let's say that we have, it's like, they're almost free. They're $0.0, right? So we could add 10 of these, and it would be like, we need to add 50 of these for it to actually cost $1. That's how cheap these are. So, and actually if I go to drone controller, you can understand for some of these, like an absolutely insane amount of capacitors. High power or something. Let's see. And PCB. Maybe I can't find an example for that right now. Okay, but some of these have like a ton of capacitors. And obviously not the ones that I can find now. Yeah, see? Filtering capacitors. Well, they're not filtering capacitors. Oh. Okay. You get the idea. Now you also understand why some of these board looks like this. So the smaller capacitor is, the faster it's going to charge and discharge. And if I have 10 smaller, it's going to be better in terms of it distributes the heat better, it recharges and charges faster, it takes more board space. But I think that's going to be a big problem. We'll see. We'll just add a note here. Add electrolytes, because many times when I can do this stuff and I suddenly like forget it, and then I routed the entire board and I was like, oh, need to reroute something. Okay. And then this is, what the hell is this? It's the, oh, it's the lead. Lead. Okay, we'll use lead as well. We probably don't have much to choose from. That's fine, but hopefully we can have a blue one or something. I'm not sure where to place it, but I'm just going to add it for now, and if we don't want it or change to something else. Might even do like a hole through big lead. It could fit the enclosure better. Or maybe not populate it, and then people can add it the way they want. Okay, I guess I'm at the wrong place now. Or lead. This is also not a great design. There's very few things, which is great. But the service is extremely good because they're selling electronics for free, almost giving it away, and make boards for everyone at no cost. Okay, so we have a yellow one, and this is an 80. So this is a bigger LED. Let's sort on stock. Yeah, so this is a very basic one. It's a red. And there's another red, and it's the green one. So should we use a blue one or a green one? Let's use the Hubei Kento electric one. That sounds Japanese. And this one, like C2293, seems to be like the first 2000 part number. So this has probably been here for some time in the part catalog. Okay, so let's add the LED. What the? That was obviously not the right thing. Did I add a 0 to it? Yeah, this is interesting. So it says out of stock, but this is a stock at LCSC and not the stock at Jlcpcb. So they probably have a bunch of them at Jlcpcb, and they're sold out on LCLC. So let's not care. And after all, it's just a LED of 060, no, 08, 05 size. And I can just switch it around for something else. You can even fit like a 0603 LED to this footprint. Okay, so the next thing, yeah, the chip, we have that. And then we have the 0 resistor. Yeah, we're not going to use that. And then the 1K resistor. 1K0603. Yeah, we're searching in LEDs. And I did something wrong. All categories, okay. 1K0603. Uni Royale, let's see. Yeah, this is almost free. We'll run with this. Now let's see if it's, yeah, so it's not the sense resistor, which is a 0.5 ohm resistor to measure the current. So this 1K resistor is probably used as in a series with the LED, I bet, to have like a very light, non-blending light. We have the sense resistor, so 1206, 015. So I really am not sure if they even have these. Let's see. We'll go to resistors, and then we'll go to low resistors and current sense resistors, because these resistors are different and smaller. Not smaller, but more precise. And let's see, we need 0.15. First of all, let's hit basic parts and see how many. Oh, nothing. So they're all gone. So this is not a basic part. So this part is going to cost us $6 plus the part, which really sucks. We could also solder these ourselves if we, because these are pretty big, or we can make them pretty big. And the bigger they are, almost the better. 0. So they don't even have them in 0.15. And this depends on what kind of current we're going to run. So we're going to run the same specs. So we should be using the same. However, we could also not. We can use 0.1 because this is added to the config when we set up the driver. Let's see what happens when we click this one. So nothing in stock. Okay. So do they have 0.2? Reset all. Apply. Like, what did I do wrong now? Now suddenly they have only 0.1. Let's refresh this. Zero 0.1, 0.2, no, 3. Okay, so they don't have it. Yeah, we can run this one. Let's just double check. This would be 0.15R. Let's just see if there is something we're missing in terms of how these small ones are named. So this is the Panasonic one. No, it's 0.15 ohms. This is the actual one. So let's head over to Lcpcb and hunt for it, because this is something we need to solder ourselves for now. But we'll try to select the similar footprint as the 0.1, which is just out of stock. And that would be this one. And that's probably a 1206 part. No, it's actually, actually really, so this is pretty nice. It's 2512 size. These are pretty big. And they look nice. Like they're white, or they'll just stand out because like nothing is white in resistors except for these kind of ones. So they kind of stand out. So 2512, I guess that was the footprint. Okay, so we'll select the same 2512 there, and we'll do 0.15 there. There are actually two different ways of typing that. So one remaining. Okay. Results 3044 and one remaining. That's fine. Let's sort by availability. I guess it has already done that. And we can look at the precision. So this is a 1% one for 3 watts from Sunyear. You can get an Ever Ohms one, which is like a more known company, but that's 5%. And you see it's really crappy in terms of giving off heat compared to this one. So this is great. 3 watts, huh? And it's almost free. Let's try this one. We'll change to something different later. Let's just sort on pricing. Yeah, the most expensive one is this one. And it's worse in every way, spec-wise. But I guess that is not always the best thing to look at, but we'll try. We'll give it a chance. And, you know, a lot of this electronic stuff just works, even though you give it the wrong components and stuff. As long as it's not used like to determine a voltage regulator and stuff like that, then it's pretty strict. But when we do stuff like this, and after all, if it's not super precise, it's going to show the wrong current, but that's also going to be okay as long as it's within the 1% range, or 10 for that matter. So we're not going to send the stuff to space or do surgery with the stuff. However, that would actually be cool. It would be really cool to actually make like a surgery robot that could do like surgery. At least I would, like, you know, just for fun. It would be fun to just try something like have it to remove like a mole or something from your skin. But I guess you need to be pretty sure about your code then, so it doesn't kill you. Okay. 2512. So we have the 2R2 resistor. Let's just have a look at this to see why this is a bit special. Or if it's just the naming. See, it's 2.2 ohms. And it's thick film. Let's see if we can find that 2K2 like this, if they use the same namings. Yes, they do. And basic part, oh yeah, it goes away. And it's back. 2.2 kilo ohms, 2.2 ohms. Right now, I don't remember what it's actually used for. We'll see. So this is 1/10 of a watt. This is voltage rating 50. Yeah. So this is lower, so it's within. This is 0.063. So let's grab this one. 2.2 ohms. Ohms? I'm not sure how to say it right. There. Maybe we should save. That's probably smart. Let's just check out the YouTube stream. To see, I'm just gonna look for if there's like a comment or something. Oh, I guess not. That's fine. Okay, let's go back. Yeah, I guess we have all the parts except for the capacitor. Let's just go find capacitor on LCOC and not be very picky about it. So let's try to find a ceramic one, which is pretty big. Let's see. First of all, let's select 50 volts. There. And the biggest one is a shit ton, 820. What the? What's? Okay, this must be wrong. Oh yeah, it is. Oh, did I? Oh, I didn't select the ceramic ones. No, leaded, not leaded. There. 50 volts. Let's see the capacitance. The maximum is, it's actually 33. I bet these are humongous. So these are all, so it's, okay, so 10. Let's remove 10. Reset. Let's see the big kahuna here. 33 and 22. Yeah. What the hell? I don't understand this. So you're stacking. Well, this one looks like a pile of like a turd, like almost 1 centimeter by 1 centimeter. We're not going to have room for this. And this is obviously the 20. Oh, this is a 22 one. So where's the 33? Yeah, that's obviously the stacked one. Okay, 22. Let's, oh, so there's 17. That's a stacked one. That's a stacked single one. Why would you do that? I guess it's because you could change it out, maybe. Okay, so here, so for 10 microfarads, let's see if you can find like the biggest one. Or, oh, yeah, it doesn't need to be that big. It's just so it's easier to solder. There, yeah, that's not even big. 1812, 2320. Just let's have a look at those. Okay, so this one is nice. It's a bit pricey, or it's like $50. So I guess it's not that pricey. This is 10 microfarad, the same as the one used by Trinamic. We could use this. Okay, so it's footprint 1812. And it costs $50. Let's just have a look again on the 22 micro. So this one is about the same price. It's actually like 40% different, but like who cares? It's still almost free. Or it's going to be one of the most expensive ones, but and it's X7R, so this is like a high quality one. So we'll just run with this big one because we have the multiple of the small ones here. So this could be like an extra one to fit. There we go. Library, search for it. There. And we'll add that here. And we'll remove add electrolyte. We didn't do that. So let's add, because it was supposed, so they had 4 of these. We're definitely, well, we'll never know. So we'll try 2 of these. 2 of the 22 microfarads, and we'll try 4 of these 1 microfarads for now. There, oh, it's actually getting kind of late. So I guess that is all of the parts, except for the parts that we're going to use in this project, like the SMD connector. SMD connector? I'm tired. FPC connector. And the 90-degree angled wire to board pin headers, or it's good, very weird name. Let's see, we can find them. So these are the connectors that will be used to attach to these stepper motors. I think I'm actually going to cheat here and just have a look. Actually, let's not try to do that. So we'll select in stock. We will sort on availability. I guess these are going to show up. And not sure. So I bet they are in the pin. It's like, why do they do horizontal sorting? This is messed up. It's like I actually want to download entire LCSE and just make my own UI for it? That would be actually great. Maybe I'll do that when I'm frustrated, or at least start to wire to board. Let's see. And then add. Sometimes when you add this stuff on LCLC, and if you add something like, oh, you see, oh, this is 90 degree, that's what I need. And then they forgot to mark the part with 90 degree, and then you can't find it. So if you can't find the stuff you're looking for, try to remove those kind of. I'm pretty sure it's not even here. It's probably, okay, it's here. Actually, I'm not looking for the, I'm looking for the 4. And then we have pin distance 254 here. Okay, so yeah, so this is the non 90 degree one. So this one just slides right into one. Okay, so here it is. Seems to be 2 different. You have the bomb lay header, male pin, blah blah blah, and you have the TE connectivity, and you have the CJT. So there's several, and the TE connectivity one is obviously the most famous one. Let's see if there's any reason to use that. So let's check the voltage rating and the power rating. But it's all a piece of metal through some plastic after all, and they're gonna take the same beating. It might be that the plastic is different and it can't heat up that much, but we're not going to live on the edge. And if we aren't living on the edge with this for some reason, or we short circuit or whatever, it's not going into like professional gear or a product like that. So I can't even see the rating for these. Sit up there. It's like, is it on here? To the right? No. And it's not here. Okay. I guess that's why it's the most expensive, because it has the most crappy. Yeah, and if you look at these connectors, there's some like corrosion on them. I guess not, or maybe. I just don't want like the very clear white plastic ones. Oh, they actually have something similar in black. Yeah, maybe not like the super yellow ones, because they look like they're old. But there's that many. So let's see if we can only view the angled ones. Surface mount. Yeah, I guess. Let's just like surface mount. It's probably something else. Yeah, it's these normal ones, or the JST style kind of connectors there. 13 remaining. Okay, so here are all of them. This is, I think this is the one I already have. Yeah. Horrible, horrible, horrible. Not horrible. $0.03. And this is 0.01. Okay. Let's have a quick look at the datasheet. And obviously you can change out these later, because what matters is the pin distance. You can even have other types of connectors. So 3 amps. And this is for 1 coil. So this will do. 2.5 amps on these. They're very square. These are not square. So we'll be using the CKMTW, probably stands for Taiwan. I think CKMTW. Yeah, there. We'll be using these. Let's add the connectors for the stepper motors. There. And let's look at the FPC connectors. So I'm not 100% sure how I'm going to do this. I really do not want to use FPC connectors with 0.5 pin distance because they are really not great to solder. However, and I actually don't think, well, maybe Jlcpcb have this. There's almost like a 0 chance that they have like an FPC connector that is that wide. Let's see. 0.5, 30, really? Is it? Apply. Okay, I applied. I click 30. Nothing's going to happen. Basic. So it's not a basic part. Okay, 30. Like, what's wrong? Let's refresh the page. 0.5, 30, and there it's an extended part. Yeah, I guess the number position doesn't exactly work. Yeah, and we want to use dual-sided, and that's not possible. What did I select here? Yeah, bottom contact. Because one of the reasons why we want to use a dual-sided is that then we don't have to care what direction the cable is. And then you exponentially grow the types of cable you can use with the dual-sided connector. It means that you can flip the cable, not obviously turn it 90 degrees, but not twist it, I mean. Okay, so let's look for the, there was one the other day that I looked at, and that's the FPC connector. Oops. There, FPC connector with 1 millimeter pin distance. And I think it was 30 positions. I'm not sure. Maybe it wasn't. Connectors, FPC, because we also need to select something that we actually can buy cables for. Because they're thinking like, oh yeah, we'll just buy a European cable. That's extremely expensive. So contact top and bottom, 164 left, that's good. And then we'll select pitch 1 millimeter, or should we do, yeah, let's do that. 10 left. See. And this one, so let's see. So you have a 4, 6, 8, 10, 12, 14, 16. 16. And they have 0 in stock, right? This one, it's actually great. This one would be great. So I want to use. So if you see the price, it's like $0.2. And I can use 4 of these. Yeah, that's going to take a lot of space. But I have enough space for that. Or maybe I don't. So I'm not sure. But then again, I have enough space on the board with the microcontroller. So this board could, it only needs a single one, actually. If I don't want to route the cable to like the next board on top. But then again, I think it's wiser to have just a ton of FPC connector or like footprints to FPC connectors to the microcontroller board, because then you can kind of choose yourself let's select this for now. Maybe we will even do it a bit differently. Maybe we'll just run the 10 one. I'm not sure. I really like the idea of having all of the stuff that's possible to use on the microcontroller broken out, because then you can use it for anything, but we'll see. Let's see. Do they have these in stock? So yeah, so these are without locks and through hole. That takes a lot of space with the through holing. This one is 10 positions. We'll see. I can also do it a bit different in terms of the microcontroller board. I can select connectors for SPI, another connector for ADCs, and do it like that. And then I would only need the ADC and the, yeah, not ADC. What am I talking about? The SPI. So like an SPI connector to it. We'll see. Let's not do that now. Okay, so we have all the parts here. We can now start to do the schematic. So I'm going to open a window, which you can't see. And I'm going to cheat and look at that. Then you don't have to look at all the back and forth. Of the different windows in EASYEDA. Okay, let's get the. Okay, so the pinout here is not the same on the schematic, but it's pretty much the same. Like there's some pins which are different, located differently, but that's fine because it doesn't matter that much. Let's start at the IREF. So let's open the schematics for the TMC5130 chip. Not the schematics. Christ. Datasheet. Yeah. Did I select an old one? 2019. Okay. That's good enough. And then we can do ain ref and see what the F. Okay. Ref. So this is the eval version of the TMC5130. As you see, it has a bunch more components, actually. There's probably a BOM list to this. So the eval board. Okay. If you don't have anything to look at, you need to look at the stuff that's in here, which is harder because you just can't copy something easier. But it's, you know, it's usually worth the read to see it because there's like they do some things for a reason, right? So what's the pin? Okay, let's search for ain. Did we find that? Maintain. Let's add a dash or space. Gain, drain, certain. So yeah. So this is something that's also usual, is that they have like different names in the data sheet depending on when it's made or whatever, or is slightly different. So let's have a look at the. Let's close this, include this, and this. Not this, but this. It's pin 30. Now, what is pin 30? So the pinouts are usually at the very beginning. See, pin 30 is called EN. Okay, I guess the search function in PDFs. This has happened actually many times. Doesn't always work. I'm not sure why. Let's go read what this pin is. There. Analog reference voltage for current scaling, optional mode, or reference current for use of internal sensor resistors. So the chip actually has internal sensor resistors, but we are having our own. So that means it's an analog reference voltage for current scaling. Okay. Yeah, but it's not used. It's just grounded. And I guess it needs to be grounded because it's optional. So this is something that you might miss because it doesn't necessarily say here that it should be grounded. Maybe it says that somewhere. Let's search for that. Yeah, you can use this input with a DIC from a microcontroller to change the different current scaling. Oh, yeah. So here you see selected sensor resistors. Here, this is like the absolute minimum, 0.1, and then you can pull 2 amps. Value excess upper current rating. But with 0.15, it's 1.35. We could also add 2 of these, like in series or parallel, if we want to use Jlcpcb. We'll end up at 0.20, so just 1 amp. You could add 2 in series. Okay, let's not go there. Maybe end up having like 40 resistors to find that. Let's go back to the here. So we're going to use these kind of symbols even for ground. The reason for that is that if you look at the ground symbol, it's freaking huge. So if I place this next to this, it's like, oh, that's nice. Guess not. At least we can do this. And we're going to change the font for now to monospace. Yeah. I guess that's fine. And this was not the right one to ground. So it's the AIN ref. We'll pull that to ground. Actually, we should look at this at the same time. So you see, there you see that's the wrong data sheets. It's this one. This there. So CLK. Now what's CLK? It's up here. It goes to CLK 16. It's broken out. Let's have a look. CLK 16. Oh, I didn't find anything. Okay, let's go to the top of the document and go to the pinout. Okay, here. CLK, pin number 2, CLK input, tied to ground using short wire for internal clock or supply external clock. So, because this controller needs some kind of oscillation circuit, it has its internal clock. But you could also use like a super precise external clock, or you can actually use the clock for the microcontroller. You can also share a clock with another driver, but we are just going to tie it to ground for now, because from my experience, that is good enough. I could obviously add the option to add it to the internal clock of the ESP32, if that's even possible. I think it is. With the V-Rover, I'm not sure. We'll see. So we'll just tie this to ground. There. Okay, so the next pin, CPI. Where is CPI? Okay, it's the 22 nanofarad. Let's go check out what that is. CPI. Charge pump capacitor input. Tied to CPO using 22 nanofarad 50 volt capacitor. Okay. Let's see. 22 nanofarad, and yeah, that was a 50 volt one. And then there are two ways of doing this. Either you can just add like another flag like this, and you can do this. So you have one you call CPI like this. So this is usually nice to do with the decoupling capacitors, because there could be many decoupling capacitors, or with like the capacitors supporting the main voltage, because that would be very messy to attach like to this. But for now, or at the beginning of a schematic, I just add it to schematic like this, because then it's easy to see that it's attached to here. But if it gets messy, we can just move it. There. Yeah, and we need to remove CPI and add ground. And this should probably also go to, it shouldn't go to the ground, it should go to CPO. Almost messed that up. And you see now that, CPO is way over on the other side. So we could run that wire all the way up here. That would be really messy. So what could we do? Well, we could do this. CPO there, and then we'll add CPO on the other side like this. And it's always nice to just drag it out to like this, just to check that it's actually connected, because sometimes, EASYEDA mess this up because it might be misplaced for some reason. Could be that the schematic symbol you're working with is made in another, like non-metric or different snap size. Maybe they have fixed this issue now. I'm not sure. However, then if you just drag it and up comes the green wire, it means that it's connected. Next is CSN CFG3. Okay. And that is CSN, cable select for the SPI. Let's just have a look at the datasheet. SCN shape select. So what I like to do, if this is attached to another board that uses different naming convention on the SPI, I tend to just keep the one used on this chip, because that makes the most sense to me. And then I'll change, because usually you work with a microcontroller many times, but you don't work that many times with like an external chip like this. So it's easier to remember the chip, the naming convention of the microcontroller compared to an external chip that you don't use that much. And then we have DRV ENN. And what's that? That is enable input. The power stage becomes switch off. All motor outputs floating when this pin becomes driven to a high level. So if this is driven high, it stops. So DRV ENN. This one, if this was like a bigger driver, we could break this out so we could add like a manual, like an emergency switch. We might do that. But we can also do that later. It depends on how much room there is or space on the PCB. Okay, so we have the encoder inputs, the ENCA, ENCB. We're not going to have a look at all of those because then we're going to use a lot of time on this board. For now, I'm not going to break out the encoder. If there's room for it, we will do that on the center or whatever is the closest. Next is the ref L. So these are the endpoint switches. So when you home the drive, it could automatically stop when it hits one of these. So you would have the most precise way of shutting down the motor. You could obviously route the end switch to the microcontroller and then check for a low input when it hits, but that would add some latency compared to just running it directly to this. So we have the CSCK, and that is the clock for the SPI. And let's call that CSCK. And what is it called in the Bob datasheet? SCK. Okay. And we have the SD mode. Which is, yeah, so this is, we're going to have a look at this, what this means. Yeah, it's actually now. Okay, so this is connected to the two zero resistors. One is routed to VCC IO or 3.3 volts, and one is routed to the ground. So this means that if SD mode is routed to 0 or to 3.3 volts or high, it's going to do something different. And what kind of different is that SD mode? Let's search for that. SD mode selection input with pull-up resistor. When tied to low, the internal ramp generator generates step pulses. When tied high, the step direction input controls the driver. Okay, so this means if this is tied to high, it's going to be a boring old step direction interface. Are we going to, do we want to control that? I guess not. We could do the same if we have space for it. So you could actually do that if someone wants to do that. But for now, we'll just ground it. And now we have the SDI for the SPI bus. And we have the SPI mode. Guess what's that? That is for, well, this is tied to VCCIO. So this is, are you going to use the UART or are you going to use the SPI? And we are going to use the SPI. So we'll tie this to VCCIO. VCCIO. There. Oh my God, it's getting very late. Next is SW cell. And is that here? SW cell. Yes, it's tied to ground. Let's figure out what that is. SC cell. This is based to slavery. Yeah, it's to enable UART mode, SV, so we're not going to use UART. We'll add it to the ground as well. And TST mode, probably not. Not TST mode. And then we have the bra, the famous bra, and the famous BRB. Probably doesn't stand for be right back. And it's probably not that kind of bra. This is the sense resistors. It's the bra or burb. Bra, burb, burb. Okay, bra. I'm getting tired, so I'm not funny. Bra. Just rambling. Let's see what. Sense resistor connecting for coil A. Place sense resistor to ground near pin. Add an additional 100 nanofarad capacitor to ground. It's recommended for best performance. Do we want best performance or do we not? No, I guess not. This is something we could have added if we want. So what we could do is that we could actually make a note that says if space add 100 nanofarad to senseless for best performance. I'll just put it down here. Okay, sense resistors, sensors. That sound like a band. Sensors, the sensor sisters. Okay, not funny, maybe. Let's just pull that up like this for now. We'll run this straight to the bra. This straight to the PR back. And we'll pull it to the ground. There. Okay. Yeah, it doesn't look beautiful. See, this is like one of the reasons why I like to make my own schematic symbols, because then I don't have to do like this. I could have just placed the resistor like in a nice way, like, you know, like this and this, but I can't. Or I can, but it's not gonna look right. But that's fine for now. Okay, so encoder. Nope, no encoder for you. SDO is highly practical when you use SPI bus. It's the data output. And then we have SVN and SVP, diag 0, diag 1. So what are these? Diag 0. Okay. Diag 0. Oh, just noticed I said push pull. Let's find the diag. Diag, diagnostic output, interrupt or step output for motion controller. Use external pull-up resistor with 47K or less in open drain mode. Single wire negative only with SV cell 1. But what is SV cell? SV cell single wire interface mode. Okay. Single wire interface, select input tie high for use of single wire interface. This is the UART. Only when SPI mode integrated pull down resistor. Okay. So we should use this pin is actually broken out. It's because this pin will go high when shit hits the fan, when the drive has some sort of error. This could be practical to route to the microcontroller. However, if you're going to drive 6 of them, it would take up 6 I/O. But we could also run all of them to one single I/O, because it might be better to notice really fast that something has crashed instead of reading the SPI of all of the 6 or 3 drives. So we're going to add this because we're going to use it. We might just route all of them to a single I/O. Depends on how much space there is, but probably just to a single one. And this is it's N, or no, it's not N, it just looks like an N. Okay, let's see what shenanigans they have done here. Oh yeah, they have broken it out. Diagonal. We don't need to do that. Position compare or dire output mode for a motion controller. Use external pull-up resistor in open drain mode. Okay. Let's not use it. Okay, and then we have VCC IO, which is fairly simple. And I haven't actually, yeah, there it is. And then we have VCP. What is that? VCP is, where is it on the BOB? Okay, it's attached to VS2 and 1 and VSA. Interesting. Let's see. VSP. Charge pump voltage. Tie to VS using 100 nanofarad capacitor. Okay. 100 nanofarad. There. So we are going to do this. Let's add it out here. There. And all of these will be added. This is the VS. This is the motor driver voltage. But what is the VSA? So you see, this goes straight to the VS. What is VSA? VSA analog supply voltage for 5-volt regulator. Okay, so there is an internal 5-volt regulator normally tied to VS, provide 100 nanofarad filtering capacitor. As the chip uses 5-volt logic for some of its internal circuitry. It goes out through the 5-volt output of internal 5-volt regulator. Okay. Yeah, that's what it does. So we need to add the VS. 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 That sounded as a yes in Russian. 5-volt out. Okay. Is that going to be used? Yeah, this is 5-volt out. Goes straight into VCC. So that means that In this driver, it's using the internal regulator for 5 volts. However, we could also use a 3.3 volt regulator. That is what I did last time when I made this. The reason for that is that I didn't want the heat that it's produced when you step down the voltage from, let's say, 40 volts or whatever, down to 5 volts, because it uses like an LDO, like a resistor. And that's going to dissipate a lot of heat. But we are not going to care about that now, because this board is going to be low power. It's probably going to handle enough of the heat it's going to produce. And it's really not like we try to save on what we can save here, or what's, sensible. Yeah, I can remove this now. I don't need that now. So let's see. 5 volt outs. We'll just use the same. 5 volt outs goes to VCC. VCC. But what is VCC? Is it the same as VCCIO? Nope. This is something else. It also has 5 volt out flag, so that means that this cable will be named, or wire will be named 5 volt out. So, yeah. Okay, it should be tied through that 2 ohm resistor, and it should have these capacitors as well. Let's not forget that. So let's add these. So let's get the 2.2 ohm resistor. Let's pull this out. You see, it didn't connect. There. If I would just left it there, that would be kind of problematic, because I wouldn't notice, and I might get like an error, which I would have some problems finding. And then we have the 470 nanofarad capacitor. Probably going to redo this later to make it look nicer, but for now, we're not going to care too much about that. There. Let's see if it looks the same. Out through 5 volts, through the resistor, through VCC. I did a mistake. 470 nanofarad is connected to VCC. However, the 4.7 microfarad is connected to 5 out. So it's connected before the resistor. So let's just move this out of the way and just redo it. 4.7 goes there. 470 goes there. There, and then we are actually closing in. There. There we have it. Yep, that's more like it. Okay, so now is the OA1, OA2, OB1. So these are the stepper motor connectors. We'll go here, OA1. just copy all 4 and just rename them OB. So they're called OA1, OA2, OB1, and OB2 4. There. And now we have a ton of non-NC. Why do we do that? Why do they provide a ton of these NC non-connected ones? Let's save that for the end. Let's ground the rest of this stuff here. The E pad that's a very big pad on the back of the chip. There. Okay. Oh, I suddenly started to search. However, there are some stuff here that's left that I haven't touched. Yep, that is the connectors and the rest of the 100 nanofarad resistors. So we have forgot something. Yes, we have forgot the resistors. Or actually, we haven't. We are going to set these up a bit different. Because, like I said, there's many of these, or it could be. We're going to add this just a bit differently. We're going to do like this. So we'll add the filtering capacitors like this. And then we'll do the same with the resistors for the main input power. All of these. And because it's getting a bit late, I'm going to be a bit lazy. I'm just going to ruin the C11 like the nice numbering, and I'm just going to copy it along with the VSN GN net flag. So we wanted 4 of these, or at least that's how I remembered it. There we are very close in finishing the first version of the schematic. Obviously, we need to figure out how we should route the microcontroller. But at the very end, we're just going to take a look on how this is going to look on the PCB in terms of how much space it's going to fill. So the LED, where does the LED go? Yeah, it goes to VCCIO and to ground. We could also add a LED to enable. I think that makes more sense because it's more important to see that it's actually activated rather than to just see if it's it has I/O voltage. So we're actually going to do that. So we'll differ a bit from the design of the BOB. And if I read it correctly, it said that this is high. Let's see. N TRV enable input. The power stage becomes switched off when this pin becomes driven to high level. It's the opposite. So it turns on. So that means that we would need to have like an inverter circuit in order to make this work. So for that reason, I'll just rename this to VCCIO for now, because we don't want to look for an inverter circuit for this, because we would need to have inverse logic for this. Okay, and there are 2 filtering capacitors that is missing. Where did we? Yep, make 2 2 of them should be added to the main power rail, the VS. Because you want to have some of the small ones here as well to provide for those really short bursts of power usage. Okay, so if I run a check now, like a design check, let's save. And you see there's like some, it's like, what's this? What's this? It shows there's some errors, some of them because we haven't added. So for example, this, I haven't added the connectors for this. We can do that. Let's just do that really fast, because at least we'll get rid of these for now. So now I've added the connectors, the net flag, which showed up as an error. See, they're gone. Now we are gone with cable select, our left, diag 0, drive engage, enable SCK, SDI, and SDO. That is from memory, everything we need to connect. We should also connect VS. We call it VC there. Okay. That's not the right. It should be VS. And now that became fixed as well. However, this should be added to a big connector as well. Let's not forget that one. Let's, I'm gonna cheat and not browse for that, because I have that right behind me. So that is, actually, I don't, because I'm not gonna use the 3.8 millimeter versions. So we need to head over to LCSC for the last time and find the right one. So we'll go to connectors, to pluggable system terminal blocks, to 3. No, not 3.81. We are going to go to, yeah, actually we are. And I actually have the right ones here. I'm just too tired because it's the 5 millimeter we're not going to use. So it's the C7245. Let's search for this, and then you'll at least get to see. This is how this looks. Place this here. I have. What did I do here then? What the? No. Yeah, I'm not going to use this green one there. I'm getting too tired. This is for the main power, and that is going to be a double version of these. So not 4, because we are going to add multiple of double ones. Position per level 2, and then we're going to select Ningbo Kangnex Electric, and they're going to show up here. This is the 5.01 millimeter version. We're looking for the 3.81 there. Okay, let's grab that. C8387. Because this is going to take up a lot of the space. We are actually going to add many of these. We're not going to add many connectors. We're just going to add a bunch of footprints. Because if you want to stack these on top of each other, you don't want necessarily to have these ones right above each other, because that adds more height than we actually need. So let's add ground to one of them and VS to the other one. Okay. Okay, so we're done. No new errors. Let's as the very last thing we do, before we start with the PCB, we're going to do we're going to skip the net check because we have already done that. There is no PCB under this project. Would you like to create one? Yes, I would do exactly that. Okay, start X. Yeah, I usually just hit whatever. Yes, and then we'll just start over. Or I could actually, because I know the measurements here, so I can just, oops, pull this outline. Yeah, I'm gonna, oops, I don't want to do that. I don't want to, M. Okay, I want to select it and then move it. That doesn't work at the moment, or let's hide the left sidebar here. There we go, and I'll just add it approximately to the center, because then I can do this. Minus, I can just change the start X point, and everything will be great. However, I'm actually not going to do that. I'm going to do something even faster. I'm going to adjust the snap size to 30 millimeter for now. However, I'm not able to recreate the complex outline pattern in this stream. But now it makes it really easy to make like 60 by 60 millimeter circle. Okay, so this is the size. So let's just do a very quick check here to see if this is even possible to have 3. Let's do snap size 1 millimeter. What the heck is this? It's like they added a bunch of measurements as, oh yeah, it's just a comment or something. It's like document. Let's remove that. Okay, so, and we are also going to remove some of the side here for the FPC connector, but that's fine. Let's just add one to the center actually. And then we have this connector, which needs to sit. So at the moment, we'll just test fit everything. We're not going to care too much to get everything right here. Like that. This one should have all of the placement back here. Let's remove all of these capacitors. Like this. And as you see, this take up a lot of space. Now we're just going to very quick. But however, we don't need to have this amount for all of the drives because they're obviously not, well, you can max everything out at the same time. But realistically speaking, you're probably not going to do that. We can also just go back and change the size of these components if we see that, oh, this is like ludicrous in terms of how much real estate we are actually using for this. And we probably need to change something. So here we have the really humongous sensor resistors. We'll just place them like this for now. And I guess they shouldn't be placed too far from the chip. However, it's not going to make that big of a deal. This is not for a rocket ship. And we could, have someone which is a lot smaller. If I place them really close to the chip like this, could be a bit dangerous because we could actually short everything when we're soldering because it's easy to hit the chip, and we don't want to ruin like a $10 or $5 or $3, whatever it's going to cost chip because we messed up with the soldering iron. Believe me, I've done that. when I say this stuff, I don't say it because I think you're stupid. I'm saying it because, yeah, I don't need to finish that. I've obviously done the same mistake. There, let's just move this closer. Something like this. And then we have all the other capacitors. We have the lead. Let's just put this, whatever, there for now. Some more resistors. So obviously this is probably not the right, yeah, I can't place it inside the big resistor. We'll just leave it there. And then, but you can notice, like, yeah, this is for the LED. Keep that out of the way. But you see quite fast that, like, the designers of the chip spent a lot of time in terms of where you should, add a lot of this stuff in terms of the pinouts, right? So it's like, yeah, it makes sense. All of these filtering capacitors should be really close to the chip, and they are going to be added with the SMD process through, the SMD soldering process. I'm not going to care too much where I place this now. Okay. These are obviously not placed necessarily here. Okay, so, yeah, whatever. As you see, there are 4 big problems here. Sense resistors are huge. These capacitors are pretty huge. But it might not necessarily be a big problem because we can move the chip down here. The shorter these tracks are, the better, because these tracks are going to have the output voltage for the motor, and they will vary in current and voltage all the time and oscillate and do all kinds of shenanigans and cause EMI and that stuff. So it should be as short as possible. So are we able to add 3 of these to one board? And also add the FBC connectors, okay? Yeah, probably. We're going to use a 4-layer board. We have a lot of the stuff we can actually remove, like the capacitors here. So what we could do is that we can save up all of these capacitors, and we can add them at the very end where we see, like, okay, so there's a lot of space here. This is not used. And then we can just go and edit the schematics first. I always like to edit schematics first, and then remove the parts from the PCB by updating the PCB from the schematics, because then you won't mess things up and remove stuff that you haven't removed from your schematics, and then everything is gonna wreak havoc. We could also use smaller sense resistors, obviously. Like, these ones are so big that they're going to be hard to solder because they are close to the TMC driver chip. So the board is not going to be square like this, almost square, but let's just have a very quick look on how this is going to look in 3D, because maybe some of the components will be there. Okay, yep, so, all right. Okay, so very, very quick and dirty placement of these. This can obviously also be placed like this, vertical to each other. And yeah, it's so hard to not just try and do it right now, but I'm not, because it's getting really late. It's like 30 minutes to midnight. Oh my god. Okay, so that is it for this stream. In the next stream, I will be making the PCB outline for having like the complex shape that you might have seen in the thumbnail. At the very end here, we can see if I can go to Fusion 360, and we can just have a very quick look here. Yeah, now I'm in the rendering mode. Let's go out. And I'm actually selected, that's why everything is blue, the table that I added in order to make this effect of this wooden here. No, I'm too big. I mean, we can have a FP-stick connector for the SPI bus, for UART, for ADCs, for I2C, and stuff like that. Okay, so that's it for now. Thanks for watching the video or following the stream or whatever. Subscribe to the YouTube channel if you haven't. It's the live channel. And have a good night or day or whatever. Catch you next time.